My name is Dmitry Sitrakin. I'm a co-founder and EVP of engineering here at Grid Gain Systems. And today's presentation is about in-memory Hadoop accelerator. What we're going to talk about today? We're going to briefly focus on Hadoop overview. I think, this Hadoop meetup, lots of Hadoop folks, probably you are familiar with Hadoop. We're going to talk why we need acceleration for Hadoop, why it is slow, and what we need to do to make it faster. We're going to, probably many of you know about Spark, so we're going to do a comparison with Spark and see how we're similar, how we're different. Then we briefly will cover a customer use case that we went through recently, and then move on to Q&A. So overall, I planned for about 40 minutes of me talking, and then as long as it takes to answer questions. So before I proceed, want to announce some news. On February 28th, our company went open sourced all our code base. Essentially, we had 4 additions: Data Grid, streaming, accelerator for Hadoop, and the whole, in addition that has it all, it's called Platform Edition. So all of that is open sourced. We picked one of the most liberal licenses out there, Apache 2 license. We're available on GitHub. You can actually fork us on GitHub, take a look at what we're doing. We did it in the hope of building actually community and growing with the ecosystem. So we're hoping that with more and more people finding out, the community around our open source product will grow. And we do accept contributions, so you can, in a standard way, so you can actually fork it on GitHub, do some coding with it, and back a patch to us, and we'll take a look at it. If it works, if we can test it, then we'll, and if it makes sense for the product, we'll integrate it into the product. We have two sites. One is commercial, one is open source. Open source has lots of features. Pretty much all the feature base that we have went into open source edition, except for some features that have to do with extreme scaling and availability. Those are still enterprise features, like data center replication, or replication of data centers across one, rolling updates, hot replicas, etc. So certain high availability features are remaining in enterprise edition, but with open source edition, it has enough feature to go in production. Moreover, we even include management and monitoring into open source. Majority of vendors, when they open source, they keep management and monitoring close. We have 2 components to management and monitoring. One is console-based, which is open source, and another is GUI-based, which is closed source. So the console-based monitoring is actually included into open source project. And this is actually very important for any grid-enabled project, or product, for that matter. When you start up like 10, 20 nodes, you immediately get lost what's where. Something is going on there, something is going on here. So you need one centralized view, on, at least on your cluster, to find out the metrics, find out the overall load, heap utilization, cache heat, miss ratios. All that stuff is provided in the management and monitoring console, which you can also work with when you use our open source edition. So before I go into Hadoop overview, I want to ask a few questions for you. How many of you actually work with Hadoop on daily basis? All right, good, good. How many of you run into performance issues with Hadoop? One hand. How many of you using Hive? Any performance issues with Hive? More than with Hadoop, yeah. And Pig users? Any Pig users here? You use everything. All right. So that's actually this presentation is about Hadoop acceleration, and we get, the feedback we get from our customers is that lots of times Hadoop jobs take too long to start, take too long to run. Especially lots of complaints about Hive being slow, queries running slow. Same for Pig, and the bad thing for those customers is, there are products that accelerate SQL, but they're not Hive compliant. There are some products that are Hive compliant, but they cannot load the whole data set to work with. So there are solutions out there, but they don't work for them. And that's actually the reason why we started this Hadoop Accelerator project. And one of the reasons we're actually doing it is to help those customers. So let's take a look at, let's start with Hadoop overview. Let's take a look at what Hadoop is. first and foremost, Hadoop is a batch system. For better or worse, it was designed from the get-go not to run in any kind of real-time environment. The main purpose of Hadoop was, if I have an analytical job and I have lots of data, data is distributed across a file system, distributed file system. How do I analyze it? And the performance never mattered. It never was the question with Hadoop, how do I analyze it fast? With Hadoop, it was more of a, how do I actually get results back? And that's why Hadoop was built from ground up as a batch-oriented system, and it never had any kind of performance concerns or characteristics in mind. Two major components of Hadoop is HDFS and MapReduce. The majority of you working with Hadoop, you probably already know that. Most of the code in Hadoop is about HDFS, and then MapReduce is almost an add-on on top of it to process data that resides in HDFS. Hadoop has a very rich ecosystem, as we all know. I mean, Hadoop is just not just Hadoop. There's lots of products written on top of Hadoop. Some of the most famous ones are Hive, Peak, Mahout, HBase. There's probably many more that I'm leaving out. And I think we can all agree that it's probably the most popular and the safest choice for any kind of analytical processing today. So it's growing, it's enjoying very good growth, and more and more businesses are picking it up as their tool of choice for analytics. So let's take a look at Hadoop pros and cons. So one of the good things about Hadoop is that it scales very well. Hadoop does have a performance issue, but it does not have a scalability issue. There are known clusters of up to 500 and above nodes in Hadoop, all deployed and worked all deployed in production and working well. Hadoop is fault tolerant. Fault tolerant means that if one server crashes, another one can pick up the load. The data is replicated across the cluster. Usually by default, Hadoop has 3 replicas. So those are advantages. So it can actually process, by distributing data across the cluster, it can actually process it in parallel fashion, which is that's why it's very popular for analytics, for MapReduce kind of processing, because it can actually process terabytes of data. And again, ecosystem we would put into pros category, because it is definitely a good thing that Hadoop is enjoying such a good growth, and the ecosystem around Hadoop is also growing. So let's look at cons. So what's bad about Hadoop? I would put batch-oriented processing as a bad thing, as a cons. If you design your product from ground up to be fast, then it can be used in both environments. It can be used in batch-oriented environment and in real-time environment. If you design it to be only batch-oriented, then you cannot use it in a real-time environment. So I do not know why Hadoop, when they started working on that project, isolated the use case into batch processing and didn't want to focus on real-time processing. So the fact that Hadoop is batch-oriented is good, that it can process batch jobs, but it's bad that it can only process batch jobs. Fairly complex deployment. Hadoop has lots of pieces. There's a job tracker, task tracker, HDFS data nodes, then there is a name node, then job submitter. All those pieces interact with each other. All of them are doing something. So deployment is fairly chatty and fairly complex. No embedded execution. So there's a point here that I want to make about embedded execution, that Hadoop is all about collocating your executions with data. Whenever you run your MapReduce job, your mapper will try to see, will contact the name node and ask them where are these pieces of data located. Name node will tell, the topology on which this data is located, and then the mapper will run on those nodes. However, it runs outside of process. Every time a mapper is a separate process, HDFS data node is another separate process, and disk is yet another, we can call it another medium where processing happens. So essentially the data, even though two processes are running on the same server, they're still not running one inside another. It's not embedded. So you're essentially bound to the bandwidth of the local socket, of the local host. And that actually gets saturated when you're processing lots of data. So the local host is actually a limiting factor for Hadoop. The local communication, inter-process communication that's happening on the same server is actually limiting for Hadoop. And another disadvantage is that HDFS is I/O bound. You constantly work with disk. Disk is known for good block level access, but it's not good for random access because it constantly brings pages in and out. If you want to access a certain piece of data, you're actually required to load the whole block. So I/O bound, HDFS is I/O bound, and it's not as fast as being memory bound. So those are the reasons, actually, those disadvantages are the reasons why we need Hadoop acceleration. So again, just to summarize, HDFS carries an overhead, I/O overhead. There's nowhere to store intermediate data. When you're running MapReduce jobs, and they produce a lot of data that you only need probably for a few minutes until the next MapReduce job runs, and after that you want to discard it, you're still forced to store it on disk. And the disk grows until unless you explicitly start managing it, the disk keeps growing. So there's no point to go to disk for intermediate data. Why not just store it in memory in some place, then have other jobs access it, and after that discard it? So one of the things that our memory accelerator does is allows you to store intermediate data in memory. Hadoop is built for Hadoop jobs often take minutes. They don't take seconds. Again, I mean, as a batch-oriented system, Hadoop was built from the ground up for batch processing. The jobs are taking minutes. The Hadoop scheduler takes a long time to start up. One of the big problems in Hadoop, actually, it's not the actual processing, but it's this pull versus push approach. When a job gets submitted to Hadoop, it doesn't get pushed to the worker nodes. They query the submitter, and when they see jobs, then they pull them. The schedule would pull the jobs and start executing them. So that's why tasks take too long to start, often between 15 and 30 seconds. So if you have your Hive query generating lots of MapReduce jobs, that adds a lot of overhead. So one of the challenges with Hadoop, how can we make it real time? Is there any way to make it real time? This diagram actually shows all the chattiness that happens when you actually submit a Hadoop task. So if you look here, there's a user application that contacts a Hadoop client and schedules a MapReduce job. Then client will communicate with name node and job tracker to actually figure out where to run those jobs on. Hadoop job tracker will then schedule those jobs to run on task tracker nodes, on HDFS data nodes. So, and then those are in turn going to contact the HDFS data node for data, and the data is coming from disk. All that communication happens there and back, and name node is contacted multiple times along the way. So this process is way too chatty and way too slow. So how do we accelerate it? Like this. What we do is we avoid all those pieces and we go directly to the data node. So again, you have your user application, you have your GridGain Hadoop client and GridGain client running embedded in one process. And instead of going to job tracker, name node, task tracker, HDFS node, and then disk is not. I don't think I had room to show the disk. You go from client to the data node directly. And moreover, when you go from client to the data node directly, you don't just run on that server. You run embedded with the process that caches data in memory. So for our accelerator to access data, essentially all that happens is it's a pointer-based access. We just look up a pointer in the memory and we get the data. We never have to load blocks of data from disk. We never have to go anywhere to get the data. The data is available in process in memory, and that's where actually we're getting all this speed and all this acceleration. By the way, if you have any questions as I go, please don't hesitate to raise your hand. I'll stop, I'll pause, and we can do some questions. Yeah. All right, so the question was whether we're compatible with version 2, and yes, we are. We support Hadoop version 2 and Hadoop version 1 and version 2. And I'll be going over features in more detail on upcoming slides. So let's review. What do we have? What does our in-memory accelerator for Hadoop does? First, there are two components to the acceleration. One is in-memory file system. Instead of going to disk, we're caching data in memory. So immediate questions that I usually get is, what if my data set does not fit in memory? What if I'm having like 10 terabytes of data, and I only need to, and I only have 500 gigabytes to work with, or maybe 200 gigabytes of RAM to work with? That is okay. GridGain will cache only the hot data in memory. We have a very smart eviction policy, which will, in a lot of cases, will predict what to load in memory, and in a lot of cases, will simply evict the old least used data out. So the hottest set of data is always in memory, and it's not even the hottest files. It's hottest blocks of those files. So if you access randomly blocks from different files, those are the only blocks that will end up in a hot area in memory. As far as Hadoop goes, Hadoop Accelerator goes, all the features in Hadoop Accelerator are open source, except for a few screens on management and monitoring, which I'll show later. All the functionality is open source and free for you to try and use. So the question is, where did name node go, right? Yes. Right. So it's a single point of failure. There's a Cloudera, I think, and Hortonworks are doing stuff to make sure that they can actually fail over a name node. But yes, I mean, it was very weird from a design standpoint that Hadoop even chose having a name node, because we have other products like in-memory data grid, by the way, which is a basis for our Hadoop accelerator, which also does data partitioning and also always cares about which data is stored where. But we do it by VI function, either a rendezvous hashing function or a consistent hashing function that will always tell you where the data is without actually having to store that information. It's just a function, you plug in key, it spits out a node on the other side. And it does it consistently, so if your topology changes, the keys don't jump between nodes. They only jump to the new nodes when a new node is added, and they evenly get distributed across existing nodes. So we do not need name node. We just have a function that tells us where to go. And the cool thing is, an open source product, you can actually take a look how we did it. Yes?
Can you repeat again? I think you said, how do you decide what to add?
Sure. So there are several ways. First of all, majority of caching algorithms, eviction algorithms, let's put it this way, they're based on LRU, least recently used policy. So at the core of most of the eviction algorithms, you will have that. So we have that as well. But on top of that, we try to predict. And a lot of prediction goes into certain behavioral patterns that Hadoop tasks exhibit. One of the most obvious one, I can tell you, is let's say you're executing MapReduce. Majority of the times, MapReduce is a scanning protocol. Majority of the times, you will be scanning through certain area of data. So for us, it's not important to cache the whole thing, because the whole thing will not get into cache. But for us, it's important that whenever you go and scan through this area, this data is in memory. And that's exactly what we do. So we preload the data ahead as you scan. And if you stop scanning and you start jumping, then we stop reloading and we go there and we start preloading from a new location. So that's another one of the most obvious areas to tackle. But there are other algorithms that do predictive file access. Some of them do work, some of them don't. This one will work for sure. So two components to our accelerator, I'll just summarize. One is in-memory file system. And I'll go in some more detail about our in-memory file system on upcoming slide. And another is MapReduce. So one of the pains, so those are two pains when you actually work with Hadoop from performance standpoint, and those are two things we tackle. So together, our in-memory file system and our in-memory MapReduce together will give you, in certain cases, up to 100x performance boost. The question was, how much data, what's the ideal RAM size? So the answer is as much as you can allocate. I will actually be showing some benchmarks going forward. But our largest deployments, the known largest deployment to us is over thousands of nodes, over 1,000 of nodes. How much RAM was used in there, I cannot tell you, but I can probably say that was allotted, probably in close to probably 50, 70 terabyte range for sure. And how do you decide how much RAM, how much data to keep in RAM? That's actually a very good question. We get it from customers all the time. Ideally, ideally you want to put as much data in RAM as possible. Why would you not have something in memory if you have extra space in memory to utilize? It will give you better performance. So if I could, I would put the whole data in memory. So you're usually, when making these decisions, you're bound to limitations of your system. What is the maximum amount of RAM I can allocate for my system without hurting the other processes running? And that's your number. The more data you cache, the better performance you would get. So let's take a look at this picture. This is essentially showing the architecture of our Hadoop accelerator. So up top, you still have your analytical BI tools accessing your Hadoop as usual. Then you have the ecosystem like Hive, Peak, Mahout, what's not. And then you have your MapReduce processing. And MapReduce processing needs to access data. So you have everything in yellow is Hadoop, standard Hadoop. Everything in orange would be GridGain. So if you see here in orange, you have GGFS1 and GGFS2. And it's not that you have to have both, but it's just to demonstrate that you can use our file system, in-memory file system, as your primary storage. You never have to go to disk if you don't want to. And you get to pick and choose. For instance, you can say this folder only in memory, that folder only on disk, and maybe some folders both on disk and in memory. So when you choose both on disk and in memory, GGFS will serve as a caching layer for HDFS. So just think about it, that HDFS is your database, and GGFS is a caching layer on top of that database. And by using prediction, by using hot and cold memory segments, essentially evicting cold data out of memory and bringing hot data into memory, we're actually achieving pretty good results in the sense that majority of data access happens from memory. So the important thing to note here is that our file system implements a standard Hadoop file system interface. You don't have to do anything to plug it in other than change one line in XML configuration. So you change that line in XML configuration, and now Hadoop is still talking to the same file system interface, but going through in-memory layer. It's a pluggable piece in Hadoop product itself. Hadoop itself has several implementations of its file system. They have S3, they have local, they have HDFS is one of those. And our GridGain GGFS, it's GridGain file system, that's why it's called GGFS, is also implementing the same interface and is also pluggable. And again, it's pluggable into version 1 and version 2. The interface did change between versions. Well, HDFS is actually, from reliability standpoint, is pretty good. I mean, by default, it can allocate as many replicas as you like. By default, I think it's three replicas. So do we. You can allocate as many backups as you like for any block, file block. We distribute backups across the servers. We never say that this file is backed up on this server. Every block of the file will be backed up on different server. Potentially, there's no guarantee where it will be backed up. But why it's good? Because if a server crashes, the load is still distributed between. Because when you send computations, they can still go and process data in parallel. However, we are an in-memory system, right? So our product is in memory. So I would not recommend you to waste your memory by backing up data 3 times, like with Hadoop. Hadoop has 3 replicas by default. In memory, you usually can get away. If you're actually running this architecture, where GGFS is sitting on top of HDFS, you don't need any backups. Your HDFS is the backup, is your primary system of record. If all in-memory nodes crash, you still have your disk to get the data. But if you don't have HDFS, then I would recommend backing it up to make sure that it's resilient. But again, 3 backups would be a waste of memory. Memory is not as, you usually don't have as much memory as you have disk, so you have to be more economical with it. Let's put it this way. I'll repeat the question. Is one of the advantages of having more than one replica is to actually send the job to 3 nodes and have it still work on the same data, for instance. And yeah, that's a judgment call. Even with our approach, you can do that. You can have as many replicas as you like. But from my experience, usually you have multi-core systems. I would say in majority of the cases, you want to access data in memory fast versus worry about jobs going to multiple nodes. Because if you access it in memory fast and you have, let's say, 16 cores on your servers, you can already run 16 jobs in parallel on your server. If you have 32 cores, you can run 32 jobs in parallel. So you already got some parallelism even by going to one server. But if you need more than that, then you can actually use backups and execute jobs in parallel on multiple servers anyway, even within memory system. So that goes as far as file system. Key characteristics: plug and play, implements Hadoop interface, and can serve as a primary file system or as a caching layer on top of Hadoop file system. And you get to pick and choose. Part of the data can be just in memory, part of the data can be caching for HDFS, and other part of the data could actually remain in HDFS at all times. You don't have to go one approach all across the board. You get to pick and choose what's where. And that's actually very important because in a lot of cases when you just rely on operating system caching, you don't control what stays in operational memory and what stays on disk. It's what operating system decides it for you. If you want to fine-grain control over it, you tell GridGain, this is the data I always want in memory, no matter what happens. And this data will be in memory. It will never be evicted. It will never be removed. At the same time, you can say, this data I never want to load in memory. I only want to have it on disk. And you control that as well. So from file system standpoint, I think we've covered it. Let's switch to MapReduce. So as we know, MapReduce is probably one of the major performance bottlenecks in Hadoop execution is MapReduce, and one of the biggest problems there is scheduling. I think scheduling in Hadoop is slow, and that's one of the reasons why when you launch many MapReduce jobs, you get such delays. So what we've done is we have our own MapReduce, which runs in memory. So what we suggest is you probably have, like if you're working with Hadoop, let's say you have 10, 20, 30 MapReduce jobs. Maybe only 5 out of those are performance sensitive. Maybe 2 out of those are really suffering from performance. So just because GridGain natively plugs into Hadoop and works with the GFS as is, you can actually migrate only 1 or 2 MapReduce jobs to GridGain API and leave the rest the way it is. So other MapReduce jobs can continue working on under native Hadoop API. And the thing here is because both our file system and Hadoop file system are the same, essentially, it's a view over the same file system, they will be working on the same data. So Hadoop MapReduce jobs and GridGain MapReduce jobs will execute in parallel and will see the same data. There's no ETL required. So there's a lot of times when you have to bring your data from Hadoop into another system for processing. Here you don't have to. You work on the same data, you just plug in GridGain and get to pick and choose what to accelerate, what not to. If they run on different schedules, yeah, our scheduling would be separate, but we control that our jobs don't collide with each other. And it's not that we control, we have default policies which you can alter. For instance, we have a policy called job stealing, when less loaded nodes would start stealing jobs from more loaded nodes. We have several load balancers. By default, we use round robin, I think. Or by default, we use affinity-based. But you can actually utilize adaptive load balancing. And in adaptive case, GridGain will actually monitor the load on every node and will pick the best node for execution. All of those policies are pluggable. So you can plug your own if none of the ones we have fits. So the question is, why not just migrate all the MapReduce jobs into GridGain? The answer is probably just from work standpoint, you don't want to go all in. So you want to try one, then second, and gradually migrate all of them. So it's just, the reason I recommend it is it's easier to get started this way. And as you go, you can actually migrate more and more. Combining in-memory MapReduce and in-memory file system is the key to getting ultimate performance. Just one out of those two probably will not provide you as much performance as you would like, but combining both of them together will give you, in certain cases, up to 100x. And what are we working on is we're working actually within the next few months, we will be implementing native Hadoop MapReduce as well in memory. So you won't even have to switch to our API, you will just accelerate Hadoop as is. And the hope there is to accelerate Hive and Peak installations, because if we plug our in-memory approach into those without any code change, and we can accelerate Hive and Peak, I think the value add would be huge. I think, I mean, definitely our customers would be a lot happier. So the question is, can we do chaining, cascading, and how do we handle recovery in this case? So chaining, yes, you can easily support. You just store the output of a previous job in a file system or in our in-memory data grid, which is essentially key value cache. One out of those two is good enough to store data. Data will end up in memory, and then the next, and will serve as an input to the next job. So that's very easy. The fault tolerance part is again handled by when you add data to the to file system or to cache, it will be automatically backed up. So if a node crashes, another node still has data, and GridGain will automatically route that job to that data. If job crashes in the middle, GridGain has a guarantee that at least there's one, as long as there's one node standing, the job will execute. So GridGain will automatically fail over the job as long as there are nodes available in the cluster. And you can configure maximum hops you want to make during failover, but GridGain will try to will do its best to execute any job. Make sense? Right. So some performance numbers that we've done on our GridGain labs, our own internal GridGain labs. We allocated 10 nodes for it. We actually use these labs for customers. This is only GGFS. This is not MapReduce benchmark. MapReduce is very tough to benchmark because you have to make up a use case. You have to do some logic. Here, it's straight up file-based access, gets, puts, reads, removes, reads and deletes. And these are the numbers. You can see that, especially in file scan case, GridGain offers a tremendous benefit because of our prefetching going on in memory. So if in Hadoop it took 667 milliseconds to do a file scan, in GridGain it took 27 milliseconds. So those ones, when they add up, they actually add up to real and take too long in certain cases for Hadoop. First time you access will pre-cache it, and then it'll. When you're doing a file scan, you don't have to even pre-cache. We will pre-read read ahead all the time, so the data will be read ahead. By the time you get to this data in your file scan, it's already in memory. The question is whether it was cache warm or cold. When the test was started, the cache was cold. After first execution, it gets warmed up, but for file scan use case, that whether it's cold or warm doesn't really matter. Yes? Did you have a question? No? All right. So file create, again, GridGain is faster, but pretty much on all these file-based operations, in-memory will be a lot faster than disk. So the question is, are these numbers with synchronous persistence or asynchronous persistence? The answer is asynchronous. We batch them up and then persist them asynchronously later. There's a time window when the disk and memory is out of sync, but in majority of the cases we're dealing with read-only event-based data, with immutable event-based data, and the majority of the customers can recover from that. All right. This is our management and monitoring tool called Visor. This is the only thing that is not available as part of open source. And the cool things we did for Hadoop, for our Hadoop accelerator is, first of all, we provided a file manager. And file managers, like if you know how to use Windows Explorer, then you know how to use this thing. And it's needed essentially to load data from your local file system or from any other file system for that matter into Hadoop, into GGFS. You pick and choose which file system between GGFS and Hadoop. You pick and choose where you want to move your data and do it in a drag and drop fashion. So even if you are not using GridGain file system, even if you are not using GGFS, you can still use this tool to move data between disk and HDFS in a drag and drop fashion. And another screen here, another functional feature that we provide with our management console is Hadoop profiling. If you probably all coders here at some point, so you all did some debugging, profiling, looking for hotspots. The same thing we're doing here, except that instead of looking for hotspots in code, we're looking for long reads, long writes, long disk access, non-uniform disk access. And we report all that statistic to you, back to you. And you get to make a decision. This file is taking too long to write, or too long to read. Maybe it makes sense to load it in memory. And this file is barely accessed, but is sitting in memory. Maybe we just never cache it, offload it to disk. So you look at this profiler and you make decisions as you go. And you can actually change where the data ends up in production without restarting the system. You can just literally in our file manager drag and drop data between places, and it will move from memory to disk or from disk to memory, etc. So are there any questions? There was one question that I skipped about in-memory MapReduce. So it's pretty close to Hadoop, but at the same time, so the question was, how does in-memory MapReduce work? And the answer is, I mean, first of all, we ship with examples. You can take a look. But in a nutshell, it's pretty close to Hadoop MapReduce, except that a standard MapReduce approach always assumes that there is has to be a parallel reduce step. A lot of times, when you work with Hadoop, you have a mapper step, and you have a reducer step. And a reducer step is also executed in parallel on multiple nodes, and it actually sucks data in between nodes, and there's a lot of network traffic that it creates. We went from the opposite assumption. We assume that majority of the jobs will not need parallel reduce. Majority of the jobs will need one reducer. And if you optimize for that, then API gets a lot simpler. And if you need to have more than one reducer, you can still do it by cascading, by chaining the task and having multiple reducers in that sense. But that's the main difference, that we have one reducer versus Hadoop having multiple reducers. And the data, another difference actually, is that it runs embedded. Hadoop MapReduce will run, even though it will run on the same server, it will be two different processes. Our MapReduce will run in the same process as where the data is cached. So all the data is accessed at a pointer level. It's just literally you look up a pointer, you get the data. Okay, so let's compare it to Spark. Right? Question here, how many of you have used Spark? All right, a few hands. So I'll just briefly cover what Spark is. Spark, essentially, the message for Spark is pretty close to what we do with our Hadoop accelerator. So you could say we compete with Spark. So the message is Hadoop acceleration. How do we make, not Hadoop acceleration, they're saying MapReduce acceleration. But MapReduce at this point is pretty much synonymous with Hadoop. So essentially they're optimizing Hadoop jobs. They do that by their claim to fame is RDDs, resilient data, resilient blocks of data in memory. Distributed data? Resilient distributed data set, yeah. So those RDDs are in memory, and because of that, they're able to execute MapReduce in memory on that data, and they claim that it's faster, which it probably is. Which it is actually, not probably is. It is faster because of in-memory processing. So if you look and compare two approaches, how we differ? So one of the I mean, from my unbiased standpoint, we're different. First of all, in a way that we integrate into Hadoop deployment. So we become part of Hadoop. Essentially, when you deploy GridGain into your Hadoop deployment, you should be still working with your Hadoop deployment as you were. Your Pig and Hive, you can still working as they were. You still, if you have any processes reading from or writing to HDFS, they still work as they were. We just augment your Hadoop deployment by making it faster. So no ETL required, no extract, transfer, and load. When you work with Spark, you usually have to load data into Spark. You usually would have to take data even from Hadoop. Spark integrates with Hadoop, but the way they integrate is you still have to load data into Spark. And if you do any manipulation of that data or changes or creation of that data, now you have to remember it to persist it back to HDFS. So there's a extraction of data from Hadoop into Spark and back. Spark works with files. If we keep in memory only the hot file blocks, in Spark you work with a full file. So your full file has to fit in memory, or they start persisting it to disk. They don't have a pure caching approach as we do. So we will just sit on top and cache HDFS most recently accessed data. And with Spark, you have to actually predict, load file into Spark, do processing, and then unload it manually. And no good management capabilities for Spark. Like for when you work with GridGain, you get all sorts of views on your topology. cache hits, cache misses, CPU loads, heap utilization, what's not. We have about 15 to over 15 tabs in our visor. And plus you get file manager and Hadoop profiler. With Spark, they'll probably get there at some point. They got a big investment, but not yet, not there yet. Any questions about Spark? We are actually going to be releasing benchmark probably this month for all our editions, public, and we actually have a pretty cool framework for running distributed benchmark, which we are going to open source. And once that goes open source, we'll publish all our benchmarks. And yes, we've tried many benchmarks. I do not know if we've tried the same benchmarks as Spark did, but I will look into that. The question is what's available in open source for management. And we ship with a Scala base, by the way. We have a lot of code written in Scala for management, especially our management console is written in Scala. And it runs in two modes, command line and GUI. GUI has more features. Command line is okay to, I mean, it's minimally okay to run in production, I would say. Any questions? All right. So let's take a look at customer use case. And then we'll move to, I think we'll move to Q&A. So I mean, the customer we worked with, I think a couple of months ago, one of the very largest big data analytical companies. What they had is, they had the use case of doing a real-time in-memory MapReduce search. It's actually grep on steroids. They had to scan a lot of files, match a few strings, process them together, collect a bunch of statistics about it, and then return results to user. Where they had data kept coming into the system. They were write heavy, so the system kept growing as they were processing it. The total data set, working data set, was about 5 terabytes, and the execution time that they needed was a perceptual real-time execution. They wanted to get results within a few seconds. In reality, they were getting them in majority of the cases in over a minute, 2 minutes. So they, if we were to provide them, and we did, which we did with acceleration, that actually changes the whole business for them, for the whole business model for them. If before you click on a button, you wait for and you start your job, and it goes, you go get a cup of coffee, maybe you I don't know, check the weather, watch a sport game, you come back, your job finished. And you cannot put that online. Nobody's going to sit and stare at the monitor for 15 minutes or for 5 minutes, wait for the wheel to spin, right? So if you can execute your job within a few seconds, then you can actually put it online. You can give it to users, to your analysts, to run computations on the data and analyze the data in real time. So that was the goal, and their solution didn't get them there. So their deployment was about 40 servers and 3 backups for each data. So they had fairly large deployment. Not too large, not too small, let's put it this way. And once we accelerated it, so our goal was to reduce existing hardware. We could not introduce any new hardware, which we did reuse. We simply started GridGain data node on the same node as where Hadoop data node was running. But one thing for them was that they did not need the whole data in memory, as probably majority of the businesses do not need the whole data set in memory. So we were able to load only the hot data in memory, migrate a few jobs to MapReduce. As I mentioned, you usually do not migrate all your MapReduce jobs at once. So the way to start using GridGain was to migrate them the MapReduce jobs that mattered the most to them, the ones that had to be fast. And majority of the jobs started running in under 3 seconds. So essentially, just by plugging it in, doing a little coding right now, you will get your acceleration. Going forward, probably within 2-3 months, we are currently working on implementing native MapReduce from Hadoop, and actually plugging into standard ecosystem products that are out there that are suffering from performance because of using Hadoop native MapReduce. So if we plug our accelerator in natively, it should accelerate them. But that's coming up. That will happen in about 2-3 months from now. So that's, I think, is my last slide, and I can move to Q&A if you guys have any additional questions. The question is, how do we integrate with Cloudera? How easy can we actually plug it into Cloudera? To my knowledge, Cloudera is not doing, first of all, we've tested with Cloudera, and Gradient works fine with Cloudera. To my knowledge, Cloudera doesn't do much to change standard Hadoop distribution from Apache. They do a lot of management around it. They actually introduced a new product, Impala, around it. But the Hadoop itself is still the same. So we integrate with it pretty much the same, except for a few permission changes and directories that they added. The integration is pretty much straightforward. The question is whether we integrate with Cloudera Manager. To a certain point, yes or no. If Cloudera, I'm not too familiar with Cloudera Manager, I should say, but if they are showing any stats about file system, since we are running on a standard Hadoop file system API, we should be integrated in that fashion. But we're not doing anything special to integrate with Cloudera Manager. Our job scheduling does not intersect with Hadoop job scheduling. Oh, I see what you're saying. So how do we, without ETL, achieve that the data gets in memory? Is that on demand? We load the data transparently in memory. You do not have to do any explicit steps to load your data in memory. Versus like with other products, you would have to say this file, and this file, I have to move from this place to that place. With us, again, it's a caching layer. We don't have to know in advance what you're going to cache. We'll cache as you go. So first access will load, and second access will just work with cache data. I would say like any kind of Hadoop performance product. I mean, we're in Hadoop performance. This product particular is in Hadoop performance area, right? In Hadoop performance market. Any company that is doing who has a claim to fame with Hadoop performance, solves Hadoop performance issue, would be either our direct or indirect competitor. I would say probably Spark would be one of the biggest ones. But pretty much any Hadoop product you take, Hadoop distro, every big vendor has a Hadoop distribution. And at some point they accelerate something. Maybe in the area where they accelerate something, we compete. But I wouldn't be able to pinpoint right now on a presentation exactly what part of Oracle, if any, which I don't think we are competing, by the way, with Oracle distros. So Spark does have a commercial backer, but just like us, they're purely open source, licensed under Apache. So the question is, how do we, if Spark, you have to actually operate either in memory or in disk. I don't know if there's a hybrid approach there. There isn't one, I'm told. So you have to pick and choose which approach you take. With us, we will, you just tell us how much data you want us to cache in memory. And we'll take care, with us, the approach is more transparent. We will load data on demand. You can still preload data, by the way. If you like, you can still preload data for processing, but we don't require you to. We will preload data on first access, and then it remains in memory for all consecutive access. Anytime you load something from memory, from HDFS, I mean, it probably will be fast. However, it's not, to my knowledge, HDFS has a distributed on disk file system. It doesn't have distributed cache at the same time. It has localized caches. I've seen that feature, and I cannot say that I have an active result for you, active benchmark. But I would say that anytime you compare memory access to memory access, it's pretty fast. But from what I know, the HDFS is not cached in a distributed fashion. It's just a localized cache for every node. I could be wrong. If I am, please call me out on this. But to my knowledge, it's a local cache. So essentially, if you cache, you're bound only to what's the difference between local and distributed. Why am I mentioning this? If you have 10 gigabyte per node, then across all and you have 20 nodes, then you can cache 200 gigabyte of data. If you only cache locally, then you only locally cache whatever is locally available. So if you need to access remote data, you're still going through disk, most likely on remote nodes. What do we do to make query processing faster with our accelerator? As I mentioned, we'll take a slightly different approach. We're taking an approach of accelerating Hive natively. So by integrating natively into Hive from MapReduce standpoint and from data standpoint, caching indexes of Hive, for instance, would not be a bad idea, which we already support, by the way. For all those in combination should actually accelerate Hive pretty significantly. So we're not looking to provide any replacement tools. Our business model, the way we integrate with Hadoop is make Hadoop itself faster, not try to actually say, not trying to say, now stop using this and start using that. So you use Hadoop, you should keep using Hadoop, but it should work faster. So the question is, if we integrate with cloud, are there code changes required? So the answer is, if you integrate our file system, then the answer is no. Our file system works just like HDFS. It's just a configuration change. If you want to utilize our in-memory MapReduce, then today, yes, you would have to write to our APIs. In a few months, you most likely will not have to. We will just integrate with Hadoop MapReduce. So the question is, are there any other competitors who are taking the similar approach to us? That's question one. And to my knowledge, no. I think if you guys find somebody, let me know. Huh? No, there are companies that doing in-memory that are doing Hadoop acceleration. And all companies that do acceleration do it in memory somehow. Even Spark. Spark does it in memory. There's very few companies who will just augment Hadoop, augment Hadoop installation by transparently loading stuff in memory. I'm not familiar with any company that does this transparent approach that we have taken. And the second question was, are we going to integrate with, are we going to integrate, so you mean merge the projects? We are going to integrate with OpenStar parts of Hadoop itself, most likely, and other ecosystem products of Hadoop. We're already talking to some Apache folks about that. So I don't want to say which products yet because it hasn't been decided, but the answer is most likely yes. The data will not be, would confuse our eviction policy. So with data coming in fast at 80% writes, how do we still know what to cache? In that particular case, the data that was coming in, not all of it had to be queried. So some of the data, or not all of it was performance sensitive, I would say. So some of the data ended up in memory, another, I don't remember the ratio exactly, but a portion of that data ended up on disk and never went to memory. And the cool thing here is the customer could control what goes where. So essentially, you specify data that goes into these folders, for instance, will always be in memory, and data that goes in those folders will not. If you make a mistake, if you change your mind, or if you feel that certain data should be in memory, nothing should change in your MapReduce job. All you should do is move data from one location to another, rename a folder, change the access policy of that folder to memory, just change the the file system parameters, and then your MapReduce job can access the same data in memory. The profiling tool, for instance, will tell you well, this file is accessed a lot and it's being accessed from disk all the time. So the step you would take is grab that file and drag and drop into the folder that is in memory. But we will not do it that's too risky if we start moving stuff between disk and memory without you knowing about it. So we tell you what to move, but we still leave it up to you to move it. So the question is, what do we do for streaming? The answer is we have a streaming product. When you talk about streaming, there are essentially two real use cases. Like there's a Storm product which handles really well the workflow part of streaming. It's like when events are coming into my system, how do I actually process them on this node? That result then goes to that node, then to that, and at the same time they somehow come together and I give a result. That's a workflow part. There's also another part of streaming, which is has to do mostly with complex event processing. With the data, since streaming data never ends, essentially, it just keeps on coming, right? So the data is coming into your system. How do I query into that stream? How do I actually find out the hottest product for the last 2 hours? How do I find out top 10 most popular products, maybe, or best the average selling price over the last period of time? Because if data never ends, then you can always query it from start to end, but those are not interesting. You want this time window. And that's what CEP use case does. So what we've done with our streaming product is we looked at the market and we saw that there is a family of products that does only CEP, and then there's 1 or 2 products that does workflow. So we decided to create a product that does both. And we integrate it with all our additions with Hadoop Accelerator, with our in-memory data grid. and with our in-memory compute grid functionality as well. So the streaming portion is there to support both use cases: querying and indexing into streams, and workflow. You can actually chain, you can recurse, you can do whatever you want with your data flow. We will be releasing the benchmarks soon enough, and I will probably be dedicating next month just to benchmarking, because I'm getting too many questions about benchmarks, not only from you guys, the cool thing is, I mean, the benchmarks will be open, and after we release our open source, our benchmarking framework, throwing benchmarks into it is going to be so easy that we want to do it in that order. First, we release the framework, which should be very usable, and it will give you nice graphs of what's where, and then you can just throw benchmarks into it, and they'll execute automatically. The business model is still, I mean, we're not reinventing on business side. We're innovating on technology usually. We're not innovating on business model side per se. So the business model is you get enterprise features. If you take, like, for instance, our data grid, one of the biggest features that in an enterprise edition is data center replication. Data center WAN-based replication. If you have two data centers, how do you make sure that they stay in sync? You have availability, rolling updates. How do I upgrade between versions without bringing down my system? How do I recover from disk? All those recovery and high availability features will still remain enterprise. So you probably should expect some security and availability features of that nature when you have very large deployments coming in Hadoop edition as well. But for now, the whole Hadoop edition is open source from that standpoint. Only a few management screens that are closed source. Hazelcast, yeah, I know, it's an in-memory data grid company. To my knowledge, they're not doing any Hadoop acceleration. It's an in-memory key value store. I know them very well. So it's an in-memory key value store, and we have a competing product called in-memory data grid product, which is an in-memory key value data store. I mean, and different vendors provide different features there. Essentially, it's usually transactional and usually queryable, so you can query it. But it's not a Hadoop file system. For instance, Hazelcast does not have distributed in-memory file system like we do, or any other stuff like that. What does real-time essentially mean? Real-time usually means request response. And if your request is MapReduce job, then it's how long a MapReduce job can take. And we're usually talking about not real-time, we're talking about perceptual real-time. We're talking about a couple of seconds. Something then you can actually, a human being can still take as a happening now. Let's put it this way. Does the real-time count, start counting from whenever event occurred in the real world? And it depends on your architecture, on your deployment. Generally speaking, in majority of the cases, you are not writing your operational data to Hadoop. You actually have probably some system of records either in memory, like some in-memory data grid, or you have standard database, maybe MySQL, maybe Oracle, what's not. At some point, that data gets ETL'd into Hadoop. So I would say query time, in case of Hadoop, majority of the real-time, perceptual real-time goes into how long does it take to actually get some analytical response from the data, get some query to perform, or MapReduce job to run. The event occurred probably before it even got ETL'd into Hadoop. I think I'm going to wrap up. Thank you.